Hi everybody. Thanks for tuning in to the video rundown of the review for the logs and inverses quiz. All right, so the first problem here is asking you to sketch the graph of 2 to the x minus 3 and its inverse on an xy grid. And what is the equation? All right, well, I've written the equation here. We'll get back to this in a second. First, let's take a look at the graphs. All right, so here's my graph of 2 to the x minus 3. It's just a plain old exponential function, base 2, shifted down 3 units. So my horizontal asymptote is now at the line y equals -3. So that's what that looks like. Now, if I am going to graph the inverse of this, all I have to do is reflect it across the line y equals x, which you see a dashed line right there. So reflecting this across that line means that my horizontal asymptote turns into a vertical asymptote. And this y-intercept here at -2 turns into an x-intercept. X-intercept at -2. And the x-intercept here turns into the y-intercept there. They cross on this line here. So this is the reflection, this green curve here, of this exponential curve. As I hope you know, the inverse of an exponential function is a log function. So this is some kind of log function. We can see that it has been shifted to the left 3 units, just like the exponential graph was shifted down 3 units. So let's do some algebra. So here's my equation of the exponential function, y equals 2 to the x minus 3. To find the inverse, you just switch x and y, and now we're going to solve for y. So x equals 2 to the y minus 3. I'll just add 3 to both sides, so I get x plus 3 equals 2 to the y. And the only way to take this into a y equals kind of an equation is to use logarithms. The base is 2, the exponent is y, so I know it's 2 to the y, and 2 to the y, according to this, equals x plus 3. So it's log base 2 of x plus 3 equals y. This is my inverse function. You can see that a log function shifted left would be log of x plus 3. So this x plus 3 inside the parentheses here for the argument of the log function does in fact shift it left 3 units, just like other functions. Okay, so the actual equation in this inverse notation, f -1, is log base 2 of x plus 3. Okay, change of base rule, log base 4 of 7. That means you can write this in any base you want. I've chosen to write it as base 10, log base 10 of 7, divided by log base 10 of 4. Sorry for my squished up handwriting there, but base 10 logarithm. So this fraction is equivalent to this expression right here. Okay, we're going to skip number 3 because there isn't anything like that on the test, moving straight on to number 4 about expanding these crazy log rhythms into as many parts as we can. So this is log of a quotient, so clearly we're going to have log minus log of the numerator right here minus log of the denominator. The log of z to the 10th would be written as 10 log z. This is log of a product, so I can split this into a sum of 2 logs, log of x to the 4th plus log of x plus 1 to the 3rd, and I'm bringing that exponent down in front as a coefficient, so it's 4 times log of x plus 3 times log of x plus 1 minus 10 log z. And that's it. This one is very similar structure. I have a radical in the top of the fraction, which I've decided to convert into exponential form over here. So it's the cube root of ab squared. So the cube root of a is a to the 1/3, and the cube root of b squared is b to the 2/3. So now I have exponents there. I can use those as coefficients for my logarithms. And so it's 1/3 log a plus 2/3 log b minus log of 1 minus c. This isn't the only way I could write this, nor is this the only way I could write this. Well, I take that back. This is really the only way I can split this one up. But this one could be written differently, and it would be correct as well. You could have a 1/3 parentheses log a plus 2 log b, and that would work out to be the same thing. All right, let's do this one here. We're going the other direction now, taking this long sum of logs and writing it as a single logarithm. So 2/3 log a is a to the 2/3. I have d to the 3rd. Since both of those are positive, they go on the top of the fraction. It doesn't matter that they're in different places in this sum of terms here. This one is the only one that's negative, minus this 1/2 log b plus log c. That could be written as 1/2 log bc. And so 1/2 as an exponent could be written as the square root. So there's a few other ways I could have written this expression down here on the bottom of the fraction, but I chose to write it that way. Okay, here's the other one. This one is probably the simplest of the 4 that we've talked about here. 5 log x, 3 log y, 3/5 log z. So again, the 2 positive ones are going on the top of the fraction, the one that's being subtracted on the bottom. And so a single logarithm, log of x to the 5th, z to the 3/5 over y cubed. All right. Let's take a look at these two things. This equation right here, I've got this written out on another piece of paper. To solve this equation, you have to isolate the exponential part first and then use logarithm. So I subtracted 20 from both sides, and from that, let me continue here. So here's my equation. I subtract 20 from both sides. Now I'm going to take the log of both sides. I've got log of 5 to the 3x minus 1 equals log of 80. All I've done is take the logarithm of both sides. The power rule then can be used to move this exponent from its position here as an exponent of 5 down to a coefficient of the logarithm. That's the power rule at play right there. So I've got 3x minus 1, that expression, times log of 5 equals log of 80. I divide both sides by log of 5, and I get the 3x minus 1 all by itself, equals this fraction. Don't be intimidated. It's just a number, just like any other number. It's just a number. So to get x by itself, I'm going to add 1, and then I'm going to divide by 3. And I chose to write it, just so I don't have compound fractions, as 1/3 times this sum. I could have used a distributive property. There's a number of other ways this thing could have been simplified out, but I wanted you to see all its moving parts here. To get x by itself looking like this, this would be a very good example of an exact form. However, we could have taken another route altogether. We had this expression right here, 5 to the 3x minus 1 equals 80. I could have taken this and turned this into a logarithm statement with base 5 for my log. And so since 5 is the base and 3x minus 1 is the exponent, I could have had log base 5 set equal to 3x minus 1. There's my base and exponent, and that equals 80. So 5 to the 3x minus 1 equals 80. Once I isolate x from this, then that's another perfectly acceptable way to write it as an exact value. So log of 5 of 80 plus 1, I add 1 to both sides, then I divide it by 3, and there's my exact value. Looks like I don't have a calculated version of that, but maybe I'll post that in the forum as an aside to this video. So there's my exact forms, okay? And I'm going to go back to part B now, because that's all written out right here. So this one, solving this equation for x, I combine those two into a single logarithm using the product rule. All right, I write it as log base 3 of x times x minus 2 equals 1, and then I use the snail. 3 to the 1 power equals x times x minus 2. 3 to the 1 is just 3. X times x minus 2 is x squared minus 2x. When I take this equation and set it equal to 0, because it's a quadratic, x squared minus 2x minus 3 equals 0. That gives me x minus 3 times x plus 1 equals 0. And from these two factors, I can determine that x equals 3 or x equals negative 1. However, as we mentioned in class today, technically you do have to throw out this solution, x equals negative 1. You've done all the algebra correct, but logarithms, we have to make sure that when we use an actual logarithm, its argument has to be greater than 0. I cannot have the log of a negative number. That just doesn't work in real numbers. So technically, I would have to throw out this x equals negative 1, and my one and only real solution is x equals 3. Okay, the next problem is about writing an exponential function that goes through these 2 points. All right, so I got that worked out over here on a piece of paper. So there's my 2 points. I'm going to use this form y equals a times b to the x power. And as we've discussed this a few times, and you did this last year, I know it's been a while, but anyway, so I'm going to use x and y into the equation here and write an equation for these 2 coordinates. And another equation for those 2 coordinates, okay? So I've got 6 equals ab squared. When I take this and 384 equals ab to the 5th. My recommendation is that you take the one smaller exponent and solve it for a. So I got 6 over b squared, just by dividing both sides of that equation by b squared. 6 over b squared equals a. Now I can replace a over here with this 6 over b squared. So I've got 384 equals 6 over b squared times b to the 5th. Well, b to the 5th over b squared is b to the 3rd. So that fraction simplifies down to a pretty nice little equation here. Once I divide both sides by 6, that's 64 equals b to the 3rd. Therefore, b equals 4. So I figured out what b is. That's excellent. Now I'm going to take that b and put it back into this original equation right here. B equals 4. So 6 equals a times 4 squared. That's 16. I divide both sides by 16. I get a equals 3 over 8. 6 over 16 is 3 over 8. And so there's my final equation. 3/8 times 4 to the x power. Okay. So there's that one. All right, let's keep on going. We're almost done. This next one is kind of a joke. Writing that using the product rule and the power rule. It gives you baloney or Bologna. All right, when do you use a logarithm to help you solve an equation? Only when the unknown is an exponent, and only after you have isolated that part of the equation. Just like we did over here. When we did this equation right here, we have to isolate the part that's got the exponent before we take the logarithm, okay? Very important little detail of using logarithms to solve an exponential equation. Okay, how can you rewrite a logarithmic expression as an exponential expression? Well, that's just using the snail. That's what we do. So here's log base b of x equals y. That means b to the x. There's your little snail pattern right here. Right, there's your snail, b to the y equals x. There's the exponential expression. This thing and this thing are the same. This one is solved for y, solved for the exponent. That's what makes it a logarithm. All right, guys, I hope you enjoyed that. Be well and do some more math.